Welcome students, and in this week we are going to talk about what is ODE and what are the different methods of studying ODE. Okay, so first of all, you see we are basically working with a function. So we assume a function, let's say y is from AB, and this AB is an open subset of R, right? AB subset of R to R. It can be R also, but basically y is from AB to R is an unknown function. Unknown function, and essentially we are going to build a new kind of function using this unknown function, and any relation of the form capital F of, so essentially first of all it will depend on x is from AB, right? It will also depend on y is a function, and it will depend on the derivative of a function y prime, let's say the derivative, and it will also depend on the second derivative, and it will go on, it will depend on y, the nth derivative. This equals to 0. Let's say you have a function like this, a relation which depends on x, y prime, y double prime, and y power n. So this is called nth order. Order means the highest power of the derivative which is exist in the equation, that's called order. So the nth order equation, okay, where what is f? F is a function, f is a function which is defined from AB, clear, cross, and this n is any n can be a natural number, so I will specify all that. So AB cross y. What is y? Y depends on, see, for every x, yx is in R, so this is in R, cross y power, the nth power of y, the nth derivative of y, that is also in R, so R to R is a smooth function. What do I mean by smooth function? I mean that it is at least continuously differentiable function. Okay, so at least continuously differentiable. Okay, differentiable. So if basically what we are doing is we are basically looking at a relation like this, and as such a relation we will call it as a nth order equation, or to be very specific, ordinary differential equation. I forgot to mention this, ordinary differential equation, right? And you see, the thing is, why this ordinary? So remark, why this ordinary? Why is it called ordinary? This is because we have, basically we are looking for a function y which is a one variable function, and the domain is R, right, or a subset of R. Okay, so basically y, the domain of y is a subset of R, right, is a subset of R. Hence all derivatives involved are ordinary derivatives, right? Ordinary derivatives or simple derivatives, let's just say ordinary derivatives. Okay, so let's say if you have a function which is from R2 to R, then you have derivatives, partial derivatives, all those things are there, and in that case we call it a partial differential equation, right? Okay, so PD is what is PD? PD is partial differential equation. And what is partial differential equation? It is essentially a differential equation of the same sort of form, but here just the function, the unknown function which we will be talking about, that will be from R2 or Rn to R. Okay, partial differential equation. So deals with functions from f omega subset of Rn. N can be greater than equal to R. Okay, here n is greater than equal to 2. So basically the derivative involved will be, you see, the derivative involved will be ux, okay, uy, and so on. Okay, so uxy such sort of derivatives will be involved. So it's called a PD. So anyways, for this course we are only going to concentrate on OD, right? Okay, so let's look at this. You see here the function which we have defined. Okay, the definition, is it correct? It is not. It is incomplete definition. Okay, why it is incomplete? You see this function. So let's say for an example. Okay, first of all, A, the above definition is incomplete. Definition is incomplete. Okay, why it is incomplete and how to complete it? Let's just see. Okay, so first of all, let's just assume, and here also n is greater than equal 1. Okay, so first of all we will just put n equals to 1 here. Okay, so let's just see let us assume that n equals to 1. Okay, so essentially we are looking at a relation which will look like this. No, f of x y prime equals to 0, and f is c1, continuously differentiable c1, right? Whatever the domain it is, but it is c1. So essentially now you see the thing is, as an example you can write that, let's say f of x y prime is given by only y. Okay, now you see if you are putting y, now the equation the relation which you are looking at is f is 0, right? So essentially if f of x y prime is given by only y and then y is 0, then that is not an ODE. Okay, so it is not an ODE, right? Because ODE has to contain something about the derivative, so the derivative should be involved in this. Okay, so see, for n equals to 1, if this function has to contain the derivative, it should not be independent of y prime. Okay, so see, small note, f should not be independent of y prime, right? See, if it is independent, then it's basically a relation between x and y, and that's not an ordinary differential equation because there are no derivatives involved here, right? So it has to be some derivative has to be involved. So essentially what we are doing is this. You see, we have to modify the definition. Is a smooth function, and let me do it here, which is dependent. Okay, so let me put it this way: n greater than equal 0 and del f del yn. So with respect to this variable, the last variable, this variable, let's say if you think of it as z variable, the del f del z, that should not be 0. So basically it should be independent, it should be dependent on the derivative at least. In this case, you see, if n equals to 1, it should be dependent on y prime. So basically there should be some, so if it is a nth order derivative, it should not be independent of the nth order derivative. Okay, so nth order ODE, then it should not be independent of nth order derivative. Clear? Okay, so I hope this is clear. Okay, let's look at some examples here. So what is this? See, if I am putting, let's say, first order, f of x y prime is y prime plus 5. Okay, let's just say, then the given ODE which we are interested, ODE is of the form y prime plus 5 equals to 0. So basically you are looking at a ODE which looks like y prime equals to minus 5. Okay, so that's the first example. Let's look at a second order equation, f of x y prime y double prime, and let's write this down as a y double prime plus b y prime plus c y plus x square. Okay, then what is the given ODE? Then the given ODE corresponding to this f, right? ODE. See, this is independent. It is dependent on, say, two variables, right? Because a, I am assuming, is non-zero. Clear? Okay. So in this case, what happens is, then the given ODE is of the form a y double prime plus b y prime plus c y plus x square equals to 0. Clear? So this is another form of equation, and similarly you can also form another equation that you can of course figure it out. Okay, so please try to construct a, let's say, fourth order equation. Okay, so this is a small exercise. Let's say exercise, try to construct a fourth order equation with variable coefficients. Okay, so in this course, most of the times whenever I am saying equation, please understand it in terms of ODE. Okay, so it is ordinary differential, ODE, ordinary differential equation. Okay, because since we are always working, this is a ODE course, right? So it doesn't make sense to say ODE all the time. Okay, so this is a ODE, ordinary differential equation, right? Anyway, so now there are two forms of equation. So basically we need to study this equation. So what is the main idea of how can we study this equation? See, there are two forms. We classify this equation. Okay, so classification. Okay, so there are different classification of this. One kind of classification of ODE is this. ODE, what is it? So let's look at it. I will say that there is something called a linear equation. Okay, linear equation. Okay, so what is the definition? So nth order equation, again ODE, this is equation, is said to be linear. If the following, it looks like this: a naught of x, y, the nth derivative of x, plus a1 of x, y, n minus 1, and it goes on like this, right? And let's say a naught of x, plus a n of x. Okay, so it will look like this, y equals to 0. Okay, so if equals to b of x, let's say, if b of x. Okay, so if it looks like this, so basically you see whatever the coefficients of y n, right, the derivatives. Okay, the coefficients corresponding to the derivatives and y, that all those coefficients should only depends on x and should not depend on y. Okay, or any derivative of y. So basically it should be in this form. Okay, and then we call it a linear equation. So y basically is this. You see, what you can think of it in a more precise mathematical sense, what you can do is this. We think of it like this: define an operator. So define a linear operator. Okay, operator. So let's do it for n equals to 2. L from C to AB, okay, to CAB. And how am I defining? As L of y. Okay, so you see, I am defining a map from C to AB to CAB. So twice continuously differentiable functions. Okay, so let's say y is a twice continuously differentiable function, and what happens to y when L acts on it? So that I am defining it to be A of x y double prime plus b of x y prime plus c of x y. Okay, if I define it like this, now you see L is a linear map. You can of course check linear map, right? So please check this part. You need to check this, It's a linear map. Very easy to show that this is a linear map. So if this is a linear map, then Ly equals to some function depends only on x, okay, is a linear equation, linear second order equation. In this case, why second order? Because n equals to 2 I am choosing. You can choose n equals to whatever, 5, 10, whatever. So linear second order equation. So that is what it's linear in y. Okay, so this is linear in y. Here we are assuming that n minus 1. Okay, so here I am assuming that a naught is of x is non-zero. Okay, right. So this is a linear second order equation. Now any equation which is not in this form, will be called non-linear, Is this clear? So here also please check, this b does not depend on y, b explicitly will depend on x. Okay, so any equation which is not of this form, which form? Of the form this form. Okay, let's just call this form as a linear form of the form. Let me put it this way, of the forms star will be called a nonlinear equation. Okay, I hope this is clear. Nonlinear equation. Okay, right. So that is clear. That is clear. Now you see what we are going to do is essentially look at some examples. That will clarify things. Examples. Okay. A, the first linear equation. You see, let's write a first order equation, linear. Okay, how does it look like? You see, it will always look like this: y prime plus some ax times y equals to bx. Okay, so this is the form of any first order equation, first order linear equation, linear ODE. Okay, cannot be of any other form, that you can understand by the definition itself. Okay, so let's write down a equation. Let's look at this. You see, let's say y prime plus 2xy equals to 0. Okay, what sort of equation is it? You see, y prime, the coefficient of y prime depends on y, right? So this is a nonlinear equation for us. Nonlinear equation. Okay, and as you can understand, you see, intuitively also it is very clear that once you have a linear equation, it should be much easier to solve a linear equation than a nonlinear equation, right? Okay, because it is a little complicated in structure. Let's look at another example. Let's look at this example. Let's say that a naught of x y double prime plus a1 of x y prime plus a2 of x y equals to, okay, first of all let me write it as b of x. Now if we do that, you see, then this equation is a linear second order equation, right? Second order. Okay, and we call it a variable coefficient. Okay, because these coefficients, you see, depends on x. Okay, variable coefficient equation, linear second order variable coefficient equation, ODE. And if you see, if a0, a1 and a2 in this case, okay, are constants, then we call such an equation as constant coefficient, okay. So as a matter of fact, you see, constant coefficient linear equation. So first of all, what is the degree of difficulty of solvability? So let's say we want to solve, the question is this: we want to solve ODE, right? Want to solve ODE. Let's understand the difficulties. Solvability, I mean difficulty level. Okay, let's just put it this way: the level of difficulty. Okay, so that will actually clear up the fact that how to study this. See, first of all, linear equations are easy. Linear equations and non-linear equations, right? Non-linear equations. So this is easy, right? This is complicated. It can be easy, but generally they are complicated, difficult. Okay, it may not be solvable also, non-linear equations. Now So linear equations is easy, but it is not that easy in all the cases. Okay, now you see linear equations. Let's say that if one, let me put it this way, if one is dealing with constant coefficient linear equations, okay, constant coefficient linear equations, then it is easy to solve. Then it is easy to solve, right? Okay, that is the given. I mean, we can always solve it without a problem. Okay, so always solvable. Let's just put it this way: always solvable. Okay, and we'll see how to prove this thing. So anyways, I hope most of you already know how to do this, but we'll still go through this. Okay, so it is always solvable. Now this is 1, this is 2. If you are dealing with a variable coefficient linear equation, okay, so if 1 is dealing with a variable coefficient linear equation, then things are complicated. Okay, things are little complicated, and in some cases are solvable. Okay, so let's say if it is a Cauchy-Euler equation, okay, Cauchy-Euler equation, you can solve it, or there is something called a power series method. So for certain equations you can actually use power series method to solve it. Okay, but please keep this in mind. Generally speaking, variable coefficient linear equations are complicated. Okay, it may not be solvable. So let me put it this way: may not be fully solvable. Okay, now I should mention one thing before I go on doing all these solvable things and all. The question is this: whenever I'm saying it is solvable, what do I mean by this? Okay, that is one question. Okay, so first of all, you see, given this equation, okay, so solution of an ODE, what does it mean? Solution of an ODE, let's understand this. So you see, I will take n equals to 2. Okay, so what is an ODE? Any ODE will look like this, right? If you remember, f of x, y prime, y double prime, y power n, this sort of thing, right? Now the thing is, any solution of an ODE, what I am going to do is, for this, I mean for the purposes of understanding, I will take n equals to 2. Okay, so you see, first of all, given an ODE, so you can take n equals to 1 also, n equals to 5 also, doesn't really matter. Given an ODE, okay, how does it looks like? F of x, y, y prime, y double prime equals to 0. A solution y, okay, what does it mean? So basically, you are given this ODE, I want to find out what does it mean for a solution of this ODE to exist. So let's put it like star. Y from AB to R, it is given, right? AB to R is a solution. Sorry, this is an unknown. So that unknown function, that actually once you let's say by some method you found out something that a function. Okay, so this function, any function, we'll call it a solution of star if y is at least C2 of AB. So basically, first of all, y has to be at least twice continuously differentiable in AB, and y has to satisfy this equation, has to satisfy star for all x in AB. What does that mean? It means it means you see f of x, y of x, y double prime of x, sorry, y prime of x, y prime of x, y double prime of x, that should be 0 for all x in AB. Okay, if this is the case, then we say it is a solution. So let's look at an example. Okay, so let's say f of x is given by, let's say an ODE is given by this y prime minus y equals to 0. This is an ODE, example of an ODE, of course, right? And what is your corresponding f here? F of x, y, y prime will look like y prime minus y. Okay, so if your f look like this, then you have the ODE which looks like this. Okay, for since f is this. Okay, so given a f which looks like this, you have an ODE corresponding to that. Now you see, for this ODE, one can easily check. One may easily check that yx, okay, equals to 0 is a solution. Okay, why it is a solution? First of all, you see yx is 0. So in this case, what is open AB? Open AB is in R here. Essentially, basically it is whole R, right? Now you see yx equals to 0. Does it satisfy the equation? Is it a wise continuous differentiable function on R? Of course it is. Yeah. And does it satisfy the equation? You see, if y is identical equals to 0, y prime is also identical equals to 0. So basically y prime minus y will satisfy this equation for all x in R, right? So the second condition is also satisfied, hence this is an equation and solution. Also, you can check that, let's say yx equals to e power x also satisfies the equation, also satisfies the equation, yeah, for all x in R, right? Because y prime is exponential x, exponential same thing is happening, minus exponential is going to give you 0 for then this holds for all x. Again, exponential is twice continuous differentiable, so you understand that's the solution in this case. Okay, right? And now one thing I need you to check this. Okay, so please check that y double prime minus y equals to 0 admits a solution. Okay, you do realize that exponential x will be a solution. Can you find any other solution? Okay, and the thing is solution in this sense. Okay, so can admits a solution. First of all, of course, you do realize exponential is a solution. Okay, so this you have to check. Right now, as far as these equations are concerned, what I am going to do, so this is our main idea. So we are going to again classify it a little bit. You see, if Ly equals to Bx, okay, and L is linear, linear operator. Remember linear operator from where to where? C to AB to. So for now, I am only going to consider on second order. The same thing holds for third order, fourth order, nth order, doesn't matter. Okay, so I am only going to do it for n equals to 2 here. So let's say L equals to Bx. This is and L is a linear operator is given. Okay, for n equals to 2. So basically, what I am trying to say is this. That is L of y looks like this: a naught of x, y double prime, plus a1 of x, y prime, plus a2 of x, y. Clear? And here, of course, I am assuming a naught is not 0 for all x in whatever AB. AB can be R also. Okay. Now you see, if b of x is 0, then the equation is called a homogeneous equation. Homogeneous, in this case it is called homogeneous linear second order equation. So big name. So homogeneous. So I will use a notation, this sort of notation in this course. Homogeneous linear second order equation, let's write it as nth order equation. Okay, so that is always given, order you can always figure it out, it's not a big deal. So it is homogeneous linear ODE. Clear? Okay, now if bx is not equals to 0, then that is a not equals to 0, then we are dealing with inhomogeneous equation. Homogeneous equation. Clear? Okay, now so that is more or less the idea, huh? So essentially what we have to do is, first of all, what is the solvability thing? First of all, we have to solve for the linear equations, linear homogeneous equation, that is the most easiest form, and then we'll talk about linear non-homogeneous equation, and then from there we will go to non-linear equations, right? So that is basically the equation part. Okay, so now, so this is the equation part. Now let's look at a system of ODE. What is a system of ODE? Huh? So equations is fine, right? Now let's look at a system of ODE. What is a system? So basically we have, so I will do it for n equals to 2 here, huh? We can of course write it for n equals to 5, 10, whatever, right? So you can of course generalize this thing. This is just for understanding purposes, right? Okay. So what is the system of ODE? So any relation of the form f1 x y1 y2 y1 prime y2 prime equals to 0 and f2 of x y1 y2 y1 prime y2 prime equals to 0. Okay, here I will assume that del f1 del either one of the i's, so basically I equals to 1 or I equals to 2, that is non-zero. So basically it should be dependent on at least one derivative, huh? And again same here, f2 of del yi derivative should not be 0 for I equals to 1 or I equals to 2. Okay, is said to be a system of ODE. What do I mean by this? I mean that basically you are looking at, initially we are just looking at one equation, right? So basically one y, and then we have, you know, the solution about the equation written in terms of y and the derivative of y. Here we have two equations, y1 and y2. Okay, so is a system of ODE given two unknown functions. So basically given two unknown functions, what I mean by this is basically you have two unknown functions y1 and y2 from AB to R. So anyways, we are dealing with ODEs only. It is just ordinary differential equation, but here it is not even one equation now, it's two equations. Okay, so let's look at one example. So basically the first easy example, you see, let's write down y1 prime equals to a11 y1 plus a12 y2 and y2 prime equals to a21 y1 plus a22 y2. Okay, so this you can see that this is nothing, this is a function of f of some constants of course, and y1 and y2. Okay, and again f1 and f2 here is nothing but again function of y1 and y2, and so basically you can, if you define f1 to be a11 y1 plus a12 y2, then you have this equation and y2 prime will look like this. So this is, so the above, this is an example of a 2 cross 2 linear system. Right, 2 cross 2 linear system. So essentially what we have is you see here this sort of system. Why we say it is a 2 cross 2 system? So basically let's say if if one defines y of x, capital Y of x to be y1 and y2 of x, y2 of x, then we have already seen what is capital Y of x. Capital Y prime of x is nothing but y1 prime of x and y2 prime of x, right? So that will imply that basically you are looking at this equation. You see, y prime of x is nothing but a11, a12, a21, a22 of yx. Okay, so it is a 2 cross 2 matrix, and hence we call it is a 2 cross. And this can be written as this. You see, y prime x is a y of x, right, where a is a 2 cross 2 matrix, and then so that is why therefore it is called a 2 cross 2 linear system. Why linear? Because you see, again here all the coefficients, right, it may be dependent on x, but here, so basically here, let me put it this way, here aij depends only on x, only on x and not on y1 and y2. Okay, so you see, this is an example of a linear system. Okay, linear system. Okay, let's look at a non-linear system then. This is A, right? So look at a non-linear system. Again, I will do it for a okay, and first of all, what is the order of this system? You do realize that only one derivative is involved, so it is a first order linear system. Okay, so first order 2 cross 2 linear system. Okay, so we'll define it like this. This is just our definition, right? Now you see, the thing is, let's write down another linear system which is a non-linear system, not necessarily linear. Okay, so you see, let's write down y1 y2 prime equals to y1 prime, and y1 prime equals to y2. Okay, so you see this equation, as you can see, that this is the, if you look at the first relation, that is a since y1 and y2 prime is involved here, so this equation we will call this as a nonlinear equation. This is a nonlinear system, nonlinear system of ODE. Okay, this is a nonlinear system of ODE. This is how we define it here, because you see, again, as I told you, the derivatives, whatever it is, even if it is a system or if it is just an equation, the derivatives has to be independent of the unknown functions or its derivatives. Okay, so here you see y2 prime contains y1, so that is why, if let's say here there was no y1, okay, so this y2 prime is y1 prime and y1 prime is y2, then you have a linear system. Okay, so that's the example. Now let's look at now let's look at this thing. You see, the thing is, these systems, they are actually a much generalized version of a equation. So basically what I meant by this is, in this course we are only going to, so in this course we are mainly interested in systems, okay, and you see, what I meant by this is, of course we are going to look at equations from time to time, but generally we need to only study systems, and then the equation part is taken care of. How? So let's as an example, you see, let's look at this example. A of x y double prime plus a naught of x, let's write down a1 of x y prime plus a2 of x y equals to b of x, right? Okay, so this is an equation, is a second order equation, as a second order linear ODE. Okay, now you see, what I will do is, I can actually write this equation down as a system. So the equivalent system system. How do I write it? You see, I will write z of x. You define z of x to be y prime of x. Okay, if you do that, then our equation will actually give us that a naught of x. Okay, and of course here I am assuming a naught of x is not 0. Let's just assume that. Okay, so a naught this is for all x, Okay, so you see this equation will turn out to be z prime of x equals to b of x minus a1 of x z of x minus a2 of x times y of x. Okay, so if you look at it properly, what you can do is define another definition. Define, okay, r of x. What is the r of x? It is z of x and y of x. Okay, so therefore r prime of x will be nothing but z prime of x, y prime of x. The derivative is with the component wise. So that will be given by, and what is z prime of x? Z prime of x is nothing but b of x by a naught of x, right? Let me write it this way: zx yx plus b of x a naught of x, okay, and 0. Let me put it this way, and z is nothing but minus a1 of x by a naught of x, okay, and y is minus a2 of x by a naught of x, okay. And what is y prime? Y prime is nothing but z of x. So basically it is 1 0. Okay, so you see z prime of x is nothing but minus a1 of x by a naught of x times z minus a2 of x by a naught of x times y plus b of x by a naught of x, right? And what is y prime of x is nothing but zx. Clear? Okay, so you see, if we so basically therefore this is nothing but r prime of x equals to, let's just call this matrix as I don't know, maybe let's just call it capital A of x, r of x plus b of x. Let's just call this thing as capital B of x. Okay, so you see, I can actually reduce second order linear ODE as a equivalent system. Okay, so in this case, this is a first order. Please remember this. This is a first order linear system. First order linear system. Okay, so I can reduce a second order equation to a first order linear system. Clear? And so basically, let's say if I give you a first order linear system, can I write it as a second order linear equation? Now let's look at the converse. So given a linear system, let's say 2 cross 2 system, 2 cross 2 system. Can one write it as a second order linear equation? Okay, the answer is not possible, and you have to please find an example. Okay, so what I meant is this: if you are given a second order linear ODE, you can only think of this exact same thing as a first order linear system. Okay, so basically it's a linear system, you can think of it like this. And you see, so basically what I'm trying to say is this: if I know how to handle first order linear systems, I know how to handle a second order ODE, because second order ODE you can always reduce it. Okay, what about let's say third order linear ODE? If you are given a third order, so let me ask you another question. Okay, question. Given an nth order, n can be greater than or equal, let's say 3. Given an nth order linear ODE. Okay, can one convert it convert it to a first order system. Okay, the answer is of course you can. So please check this part again. You can. Okay, it is possible, and please check again. Please check this. How do you check it? Exactly the same sort of thing what I did for n equals to 2. Okay, same thing works here, but you have to do it for any n greater than equal 3. So please try this part. I am not doing that. Okay. So now, so essentially what we understood is essentially this is the linear system which we need to understand. Now what about second order, third order linear system? Of course those things are there, that are very complicated things. Linear systems can be anything, right? I mean, it doesn't really matter, it has to be look like that. But anyways, what we are going to do, linear systems, I mean, what am I saying? What I am trying to say is this. First order linear systems looks like this, right? Now we can of course complicate the system to a non-linear system. Okay, and then what happens is, so let me put a remark here. Remark. Non-linear systems are generally hard to solve and study, and not in any particular form. Clear? Okay, so in this case what happens is it gets very complicated and you have to do it one by one. So basically you have to look at one system individually. You cannot put a general theory behind it, okay, except the existence and uniqueness for a particular non-linearity. Okay, so essentially what we are going to do is, in this case, see this sort of system again, let's put some nomenclature down. So if you have a system like this, linear system, let's say, write it like this: y1 prime is f of, so let me put it this way, a11 of x y1 plus a12 of x y2 a1n of x y n. Okay, so there are n number of functions. yi is from ab to r are unknown. I am dealing with this sort of functions. We are dealing with this sort of functions, and this is the equation: y2 prime a21 of x y1 plus a22 of x y2 plus a2n of x yn, and it goes on like this. And similarly yn prime is an1 of x y1 plus an2 of x y2 and then ann of x yn. Okay, so if your system looks like this, then we can of course write it as equivalent system. One may write it as y prime equals to a times y, right? Y prime equals to a times y plus b. Clear? And what is a? So where? So let us put a number here. So let's say b1 of x, b2 of x, bn of x. Okay, so this is a, see, b is 0, it's called a homogeneous one. If it is non-zero, then we have an inhomogeneous equation. So where A is the matrix A I J, it is a n cross n matrix, right? And what is y? Y of x is nothing but y1 of x, y1 of x, this matrix, this vector valued function. And what is b of x? Is nothing but b1 of x, Bn of x. Okay, so this n cross 1 and this is n cross 1. Okay, so we can actually write this sort of system as a system which looks like in a compact form. This is the form y prime equals to a y plus b. Of course, a depends on x, b depends on x. Okay, so that is there, but it is independent of capital Y. This is called a linear system. So we will call it a linear system, n cross n system. So we will call such a system as a n cross n linear system of ODE. Okay, now please remember this thing. This is a linear system, general form, n cross n system. Now you can of course talk about non-linear systems. Let's say any of these coefficients aij depends on x, y1 or y1 derivative and all. Then we have these non-linear systems and all. So those are complicated things, and this is the most easy one. We will start our study by analyzing the linear systems first. Okay, so with this we are going to end this video.